Welcome to Chapter 3 of Project AEON STRATUM Prime, where we move beyond theory and into the engineered reality of advanced propulsion. In this chapter, we'll explore how ASP is not just a speculative idea, but a rigorously defined system with clear operational boundaries, stability mechanisms, and failure modes. We'll see how the system is structured, how its performance is bounded, and how it maintains safety under extreme conditions. This chapter is the bridge between mathematical abstraction and real-world application, answering the fundamental question, how is AEON STRATUM Prime actually flown and constrained in reality? Let's begin by setting the stage for the engineering principles that govern this revolutionary technology. At the heart of ASP propulsion lies the Temporal Gradient Volume, or TGV. This is not a point or a simple region, but a closed lenticular field shell where temporal gradients are non-zero and the vacuum stress becomes directionally biased. Within this shell, effective inertia is engineered and modified, enabling the unique motion characteristics of ASP. Outside the TGV, space-time behaves as usual, with no propulsion effects. The lenticular geometry is not just for aesthetics, it's a structural necessity, minimizing discontinuities and preventing edge collapse. This design ensures that motion emerges from field asymmetry across a finite volume, rather than from traditional thrust. The TGV is mathematically defined as the set of all points where the temporal gradient of the vacuum stress tensor is non-zero. This formalism ensures that only within this engineered region does propulsion occur. The equation provides a rigorous boundary, allowing engineers to parameterize, simulate, and diagram the active propulsion zone. This clarity is essential for both numerical modeling and practical system design, ensuring that ASP's unique mode of operation is consistently reproducible and safe. ASP's motion is not about pushing mass or emitting thrust. Instead, it's achieved by steering the temporal gradient field. Directional control comes from manipulating gradient vectors, modulating boundary phases, and creating asymmetric distributions of vacuum stress. This means the craft doesn't move forward in the classical sense. Rather, it reshapes the local space-time geometry ahead of itself. The result is a system with no exhaust, no sonic boom, and extreme maneuverability, all without the usual inertial penalties. The Temporal Gradient Envelope, or TGE, sets the upper limit for usable temporal gradients within the system. This envelope is governed by two critical thresholds: coherence breakdown and causality violation. If the temporal gradient exceeds the coherence threshold, field stability is lost, leading to a collapse of the gradient rather than an explosion. This means that acceleration is capped not by available power, but by the stability of the engineered field itself. The TGE is a fundamental safety and performance constraint for ASP. Net translation in ASP arises from anisotropic temporal stress within the TGV. The translation force is calculated by integrating the temporal gradient of the vacuum stress tensor over the entire active volume. This approach is frame invariant and reactionless in the classical sense, with momentum conserved via vacuum exchange rather than traditional action-reaction pairs. This is a key distinction that sets ASP apart from conventional propulsion systems. In ASP, inertia is not a simple scalar value. Instead, it's engineered as a tensor, meaning it varies by direction. The Inertial Tensor Ellipsoid diagram visualizes how resistance to acceleration changes along different axes. This allows for preferred acceleration directions and ensures that both crew and structure are protected. Importantly, total inertial nullification is neither required nor stable. Instead, partial suppression, typically a 70–95% reduction along propulsion axes, ensures operational safety and predictable control. The Inertial Suppression Envelope, or ISE, defines the safe operational range for inertial reduction. The eigenvalues of the effective mass tensor must remain within a specific range to ensure both crew survivability and system stability. Total inertial nullification is unstable, so partial suppression, typically between 5% and 30% of the original mass, is optimal. This envelope is the primary constraint for human safety in ASP operations. The Boundary Coherence Envelope, or BCE, governs how long the ASP system can sustain high acceleration and complex maneuvers. It's determined by the coherence of the Casimir lattice, which must exceed a threshold set by the difference between modulation and vacuum mode frequencies. This envelope sets the maximum duration for maneuvers and the sustained acceleration time, replacing fuel mass as the true limiter of endurance in ASP system. Unlike traditional rockets, ASP does not suffer from a propellant mass penalty or diminishing returns. The change in velocity, or delta, is accumulated as long as field coherence and gradient stability are maintained. Structural mass affects loading, but not propulsion efficiency. This means that velocity can be built up over time without the constraints of fuel mass, fundamentally changing the way we think about spacecraft performance. The formal equation for delta in ASP shows that velocity change is the time integral of the inverse effective mass tensor multiplied by the translation force. This highlights that structural mass does not penalize delta and that coherence time, not fuel, is the limiting factor. This law is a cornerstone of ASP's non-classical propulsion behavior. For ASP to operate safely, the rate of change of the temporal gradient must remain below a critical threshold. If this criterion is exceeded, the system experiences a gradient collapse, inertial rebound, or a non-catastrophic reset. This ensures that even in failure, the system remains safe and does not release stored energy violently, setting ASP apart from chemical or nuclear propulsion. ASP modifies local spacetime curvature using a localized form of Einstein's field equations. This coupling allows for local curvature effects without causing global spacetime distortion or horizon formation. The result is a system that can manipulate its immediate environment for propulsion while avoiding the catastrophic risks associated with large-scale spacetime manipulation. ASP's performance is governed by three independent envelopes: the Temporal Gradient Envelope, TGE, the Inertial Suppression Envelope, IS, and the Boundary Coherence Envelope, BCE. Each governs a different aspect of operation: maximum acceleration, cruise survivability, and maneuver duration, respectively. Exceeding any envelope leads to a specific, non-catastrophic failure mode, ensuring that the system remains safe and predictable under all conditions. The first key engineering diagram is the Temporal Gradient Volume. This cutaway visualizes the lenticular field shell, with arrows representing the non-zero temporal gradients inside. The diagram makes clear where propulsion is active and how the field geometry is structured to minimize discontinuities. This is not just a conceptual image, but a precise engineering tool for system design and analysis. The Inertial Tensor Ellipsoid diagram illustrates how inertia varies along different axes within the ASP system. The ellipsoid's shape and orientation reflect the engineered distribution of inertial resistance, highlighting preferred acceleration directions and null zone. This visualization is essential for understanding how the system protects crew and structure while enabling extreme maneuverability. The performance envelope plot brings together the three key envelopes, TGE, ISE, and BCE on a single graph. This plot shows how acceleration, coherence, and inertia suppression interact to define the operational limits of ASP. It's a vital tool for engineers to visualize safe and optimal performance regions, as well as the consequences of exceeding any envelope. ASP's approach to propulsion is fundamentally different from rockets or jets. There's no exhaust, no thrust-to-weight ratio, and no sonic boom. Instead, motion is achieved by engineering the local space-time geometry, allowing for instantaneous direction changes and acceleration that appear to violate Newtonian limits. This is possible because the craft is not moving through space in the conventional sense. Space and time are being restructured around it. Control in ASP is continuous, analog, and field-based. There are no reaction wheels, control surfaces, or gyroscopes. Instead, stability emerges from feedback loops within the engineered fields. This approach eliminates mechanical correction and allows for smooth, precise maneuvering, even under extreme conditions. The result is a system that is inherently stable and responsive. ASP is designed for graceful, non-catastrophic failure. The primary failure modes include gradient collapse, which results in sudden inertial normalization, boundary decoherence, leading to loss of maneuver authority, and phase desynchronization, causing drift rather than loss of the craft. At no point is stored energy violently released. making ASP inherently safer than chemical, nuclear, or plasma propulsion systems. ASP's interaction with its environment is subtle but observable. The system can produce ionization halos, optical lensing, electromagnetic interference, and local gravity anomalies. These effects are secondary artifacts of the propulsion process, not exhaust. They provide valuable diagnostic clues for engineers and observers, but do not pose significant risks to the environment. To an external observer, ASP's performance seems to defy Newtonian physics. Acceleration appears to violate known limits, direction changes are instantaneous, and inertia seems absent. This is because the craft is not accelerating through space in the usual sense. Instead, space and time are being locally restructured, creating effects that look impossible but are fully consistent within the engineered framework of ASP. The core operational rule for ASP is simple. Never maximize gradients, always maximize controllability. Pushing the system to its absolute limits leads to instability and collapse. Instead, long duration, coherence, and stable control are the keys to mission success. This doctrine ensures that ASP remains reliable and safe, even under demanding conditions. Chapter 3 confirms that ASP is a geometry-limited, not power-limited, propulsion system. Lenticular craft shapes are a structural necessity, not a stylistic choice. Inertia is engineered, not eliminated, and performance is always bounded by well-defined envelopes. Failures are non-catastrophic, and observed anomalies are geometric side effects, not violations of physics. ASP represents speculative physics disciplined by engineering wisdom. With the engineering envelopes and operational principles established, Chapter 4 will move into the domains of power generation, temporal oscillators, boundary lattice materials, and scaling laws. The focus will shift from how ASP flies to how it stays flying, ensuring long-duration coherence and sustainable operation. This transition marks the next step in realizing the full potential of AEON STRATUM Prime. The temporal gradient is a core concept in ASP engineering. It represents the rate of change of temporal phase across the propulsion active region. By controlling this gradient, engineers can steer the craft, modulate acceleration, and maintain stability. Mastery of temporal gradients is essential for both performance and safety in ASP systems. The inertial tensor is a mathematical object that describes how inertia is distributed and engineered within the ASP system. Unlike a simple mass, the tensor allows for direction-dependent inertia, enabling preferred acceleration, axes, and null zone. This concept is fundamental to both the safety and maneuverability of ASP craft. The coherence envelope defines the operational limits for maintaining stable field gradients and sustained acceleration. It is determined by the properties of the Casimir lattice and the difference between modulation and vacuum mode frequencies. Staying within the coherence envelope is critical for long-duration missions and safe operation. Gradient collapse is a controlled failure mode in ASP. When the temporal gradient exceeds safe limits, the system rapidly returns to inertial normal conditions. This prevents catastrophic failure and ensures that the craft remains safe, even in the event of extreme operational stress. Inertial rebound is another non-catastrophic failure mode. If the inertial suppression envelope is exceeded, the system quickly restores normal inertia, protecting both crew and structure. This mechanism is a key part of ASP's safety philosophy, ensuring survivability under all conditions. Decoherence drift occurs when the boundary coherence envelope is breached. This leads to a gradual loss of maneuver authority, but does not result in catastrophic failure. The craft may drift or lose acceleration capability, but remains intact and recoverable. Lenticular geometry is a defining feature of ASP craft. The lens-shaped shell is not a stylistic choice, but a structural necessity. It minimizes gradient discontinuities and prevents edge collapse, ensuring stable and efficient operation of the propulsion system. The vacuum stress tensor is a mathematical construct that describes the anisotropic stresses within the engineered field. By manipulating this tensor, ASP can achieve reactionless propulsion and maintain stability. Understanding and controlling the vacuum stress tensor is essential for advanced field engineering. ASP achieves reactionless propulsion by exchanging momentum with the vacuum rather than relying on action-reaction pairs. This allows for frame-invariant motion and eliminates the need for propellant or exhaust. Reactionless propulsion is a hallmark of advanced field-based systems. Feedback loops are the foundation of ASP's stability and control. By continuously monitoring and adjusting the engineered fields, the system maintains precise control without mechanical intervention. This approach enables smooth, responsive maneuvering and rapid adaptation to changing conditions. Coherence time replaces fuel mass as the limiting factor for ASP's endurance. As long as the field gradients remain coherent, the system can continue to accelerate and maneuver. Managing coherence time is therefore critical for mission planning and operational success. Local spacetime restructuring is the mechanism by which ASP achieves its extraordinary motion. By engineering the geometry of spacetime around the craft, it can move without traditional thrust, enabling effects that appear impossible from a classical perspective. The Casimir lattice is a structured boundary within the ASP system that maintains field coherence. Its properties determine the duration of sustained acceleration and the limits of maneuverability. Engineering the Casimir lattice is a key challenge in advanced field propulsion. Phase modulation is used to steer the temporal gradient field and control the direction of motion. By precisely adjusting the phase at the boundaries, engineers can achieve smooth, responsive translation and maneuvering. Phase modulation is a critical tool for ASP navigation. Anisotropic stress refers to the directional variation of vacuum stress within the TGV. By engineering this anisotropy, ASP can generate net translation forces without traditional reaction mass. Understanding and controlling anisotropic stress is central to field-based propulsion. Null zones are regions within the inertial tensor ellipsoid where acceleration is minimized or absent. These zones are engineered for crew safety and structural integrity, ensuring that sensitive components are protected from excessive forces during operation. Frame invariance means that the equations governing ASP's motion hold true in any reference frame. This property is essential for consistent, predictable operation and distinguishes ASP from systems that rely on classical action-reaction dynamics. Structural coherence refers to the ability of the ASP system to maintain its engineered field geometry over time. This is vital for both performance and safety, as loss of coherence leads to drift or loss of maneuver authority. Maintaining structural coherence is a primary engineering goal. The operational envelope is the set of all conditions under which ASP can function safely and effectively. It is defined by the intersection of the TGE, ISE, and BCE, and is visualized in the performance envelope plot. Staying within this envelope ensures mission, success, and system integrity.